Okay, now let's take a look at how the computations are happening behind the scene. Okay, so here the what you are seeing is the 0.15, 0.25, 0.30, 0.2. These are all the weights. These weights are randomly assigned to each synapse. What is synapse? The connecting line between the input layer and the hidden layer. So every neuron, every neuron is connected to every other neuron in the subsequent layer. So here, in this case, we have input layer. In the hidden layer, we have two neurons. In the input layer, we have two neurons, and the output layer, we have only one neuron. So the output layer is the one, emitting whether the given person is eligible for loan or not. Okay, the output node is the one tells us whether, or the output node is the one produces the predicted class level along with the probability. Okay, we can say instead of class, we can see probability also. So here, this is the age of the person, and then income of the person. Here, these two values are normalized. You know what is normalization? So standard. If we did the feature scaling with that, we got these two values. You just think that way. Each neuron is assigned to one attribute in the table column. This is age and this is income, something like that. Here, the 0.15, 0.25, as I said, these are the weights randomly assigned to each the line, okay, connecting line. So now we will take a look at how this works. As I explained you in the yesterday's session, in the case of hidden layer, what happens is, one second. Yeah, each neuron in the hidden layer, I just go back here. This is what I'm taking. Each neuron in the hidden layer, it takes the two inputs. So it takes the two input values plus the bias and compute its output as this one. So here, Z is equivalent to W1 into age plus, let's say, to make it simple, W3 into income. Okay, and then the value, whatever we are getting it, that one will get assigned to Z, and that Z will be passed as an argument to the f of Z, and then here it will compute the sigmoid value, which is nothing but you will get the probability value. If you remember that image here, right? So that is what is happening here. So each neuron, it takes the input values. In this case, we have two input values plus the bias. Even for the bias, we have some weight here, plus the bias, and it computes its output as this one. Z is equal to x into W. So this is x into W1 plus W3, W3 into 0.5 plus 0.10 into the 0.2 plus W4 into 0.30. Okay, that is what is happening. And we call this as a net H1 for the sake of our understanding. And this is out H1. Okay, this is hidden layer. Hidden layer, the naming convention, we use it net H1. This is your out H1. Okay, and okay, this is out O1. Okay, so fine. So now if you look at this here, the equation here, so I'm going to talk in detail about the Z. Okay, and the Z is your W1 into I1 plus W2 into I2. So net H1 here is 0.15 into 0.5 plus 0.2 into 0.2. Okay, this is the one. Okay, 0.2 into, sorry, 0.2 into 0.1. Okay, so this one. Okay, 0.5, 0.15 into 0.5 plus 0.2 into 0.01, 0.1 plus 3.5 into 1. Okay, so this is the value computed first. So if you do the math here, you get something like this. You will get finally 0.3775. And if you apply the activation function for this value, 1 to 1 plus e to the power this value. And then next one is the W3. So the next one is W3 into the I1 plus W4 into I2. This one. First, it did for this one. The next one is this. And in this case, net H2. This is your net H2. Net H2. And this is your out H2. In this case, what happens is 0.25 into zero point 0.5 plus 0.3 into zero point 0.1 plus 0.35 into 1. So each layer, the bias will be added. So that this is the bias. Okay. This is kind of your intercept in your linear regression. That is what I discussed yesterday. And the next one is for this one, the net H2 value is 0.3925. So this one, for this, we are, the activation function will be applied. You are getting this value. So for this is the value. And for this one, the output value is this one. Here I did not specify some value. Okay, we'll say some value. And the next one is the W5 into out H1. What is the out H1? So in this case, what are the value we are getting it here? So probably I'll just put it here. Let me open an Excel file. Yeah, it is there here, right? It's 5937625. We don't have to compute it. So this is the one. It is available here. Good. Sorry. For this one, the blue colored one, this is these two lines goes to the this neuron in the first neuron of the hidden layer. For that, the after applying the activation function, we are getting this value. And similarly for this one, right? This is called your net H1. This is out H1. This is net H2 out H2. Net H2 is your 0.3925. Out H2 is your 0. This value. Okay, I don't want to clutter here. So this is the one. Out H1 is this value. The next what happens is this value into 0.40 from here. For the output layer, the input is this one, out H1 into W5. The out H1 we already computed it, plus 0.40, sorry, into 0.40, plus this 0.50 into this 596, plus the bias in this layer. In the output layer, there is a bias. In this case, the bias weight is 0.6 into 1. This value is, let's assume it's 1.055. And if you apply the activation function, you get this one. Finally, these two are coming from out H1 and out H2. When you multiply the out H1 with the W5 weight and out H2 with the W6 weight, when you add these two things, you will get some value. And if you apply the activation function, in this case it is a sigmoid activation function, you get 0.75. This is the predicted value, 0. There is a 0.75 probability this customer is going to be a profitable customer. Okay, instead of saying defaulted, profitable. As according to us, we are very particular about the profitable customer. The probability of customer being profitable 0.756. Okay, and what is the actual value? Actual value, let's say this for a specific customer, this is going to be 1, right? So 1 minus 0.56, that is what the error. You get it. So hope you understood. This is how the computation is done behind the scene. The weights are randomly assigned. We don't have a control over here. That's why the weights and biases or parameters are called parameters, not hyperparameters, because the values for the weights and bias are computed by the model itself. So now if you see here, the actual value is 0.01, the mean squared error, right? So in this case, the error is equal to 1 by 2 into actual minus predicted value. So you are actually 0.0, not 1, 0.01, and the predicted is this one. This is the error we are getting it. Okay, and so there is one input node for each attribute, and perform it to perform weighted sum, perform a weighted sum of input signals and apply an activation function before passing the output to the next layer. That is what we have seen it here. Right? It was applying the activation function here. This is the one we have seen. This one activation function. So the input layer, in the case of right here, the input layer passes the data to the first hidden layer. The hidden layer neurons perform the summation on the information passed to them from the input layer neurons. The output layer neuron performs the summation on the weighted information passed to them from the hidden layer neurons. So even here, it is doing the same thing. Okay, it is taking the value of this one. Okay, this is the one we are getting it right. 0.756. In this case, we have only one neuron is there in our output layer, so we are getting this one as an output value. Now you understood with this simple example how the computation is done behind the scene, right? The mechanics of how this one works. And next, we will take a look at the activation functions. What are the activations? Like we have seen the sigmoid function. There are a lot of activation functions are available. Sigmoid, ReLU, softmax, step, tanh, ELU, and leaky ELU. Apart from this, we have something else called parametric ReLU, PReLU. Those kind of activation functions are available. So you know very well the sigmoid function is the mechanism, or it is a S curve. In simple terms, this is a sigmoid function is nothing but the S curve. We have discussed as part of logistic regression. Okay, the function, this is the sigmoid function f of s. Okay, and f of z. This function is a mathematical function having S curve. The function is defined as follows. The threshold function outputs 1 when input is positive and 0 otherwise. Okay, that is what you need to remember it. Any value between 1 and 0, right? So it will convert any value between 1 and 0. The values are bounded between 0 and 1. You remember the logistic regression we discussed. And the next one is the ReLU, rectified linear unit activation function. This is one of the famous and popular, most used activation function in the world right now. It is used in almost all the convolutional neural networks or deep learning. It's a very popular function. Okay, when it comes to deep learning, the ReLU is one of the popular function for, and it's mostly used in the hidden layer. ReLU is used. So they'll ask in the interview. So what is ReLU? ReLU is an activation function. So it is used in the hidden layers. You need to say that, okay? And so in the case of a ReLU, the weighted sum values below 0 will pass a 0 to the output signal. The weighted sum above 0 progress gradually towards 1. See, whenever your function is less than 0, it gives you 0. If it is greater than 0 output, the value remain as it is. See, in the case of sigmoid function, it will convert any value. For example, you are getting 2, 5, 6, or 6.7, and whatever the value you are getting, it will convert, it will transform them into probability to fall between 0 and 1. In the case of sigmoid function. When it comes to ReLU, any value which is 0, it gives us 0. Any value less than 0 and 0, it assigns the value as 0. And whenever it is this function, the ReLU function, okay, I'm talking about the ReLU function, is less than or equal to 0, it assigns 0. And anything greater than 0, it leaves it as it is. It is not going to convert. For example, you have something like 255. This 255 will remain as it is. It will not convert them to fall anywhere between 0 and 1. But one issue with the ReLU function is, the all the negative values here, all the negative values, it assigns them, it considers them as a 0 or assigns them as 0. Okay. So in this case, what happens, since it converts or values less than 0, It decreases the ability of the model to fit or train from the data properly. So in that case, what happens is any negative input given to the ReLU activation function turns the value into zero immediately in the graph. So this is going to affect the the model ability to learn from the data. Okay, any value which is less than negative, that should also be taken into account. Since it is assigning zero, in this case, what happens is it is not able to learn the pattern anything which is less than zero. That is one disadvantage with this one. Negative values become zero, decrease the model able to train the data properly. This is the one you need to remember it. Okay, to solve this, there is something else called leaky ReLU. In the case of leaky ReLU, it introduces a small negative slope, so it does not have a zero slope. This helps speed up the training. Range for leaky ReLU ranges from minus infinity to plus infinity. The previous case, in the case of ReLU, 0 to infinity, but here minus infinity to plus infinity. Which one? The leaky ReLU. Look here, it introduces a small negative slope. The next one is the parametric ReLU activation function. This is given by f of x equal to max of alpha x comma 0. Alpha is the hyperparameter. So in this case, what happens is parametric p-ReLU, it gives the neurons the ability to choose the best slope in the negative direction. But here, it even in the case of leaky ReLU, it addresses the issue with the ReLU, but still there are some issue here, right? It does not, though it does not have zero slope, the small negative slope will be introduced. But even with the p-ReLU, what we can do is you can choose the best. We'll choose what slope is best in the negative region. Okay, and instead of introducing a negative slope, right? Small negative slope. What you do is you choose this best slope, negative slope on your own, right? So that is where the p-ReLU, that is when it became popular. So they can become a ReLU or a leak ReLU with certain values of alpha. So again, you have some alpha is the hyperparameter. Okay, it's kind of a learning rate. Okay, you can specify some value here. And in that case, based on the alpha value, it may become a ReLU or a leaky ReLU. Okay, so you need to choose the best value, optimal value for the alpha. The next one is tan H function. In this case, it defines the output of that node given input or set of inputs. This is for nonlinear activation function, and it contains the values -1 to +1. So this is little different. So in the case of sigmoid 0 to 1 and a ReLU 0 to infinity, and leaky ReLU minus infinity to plus infinity. In p-ReLU, it takes care of coming up with the optimal slope in the negative direction. Tan H takes the value anywhere between -1 to +1. The using hyperbolic tangent function very much like sigmoid function. The output values for weighted sums below 0 gives -1 in this case. Whereas in the case sigmoid function, any value below 0, it gives 0. Tan H function also not much used, but if you know this activation function also, it is helpful. Now the difference between parameter and hyperparameter in neural network. They'll ask you this question. So what is parameter in neural network? The weights and bias. These two are, and apart from weights, you have something called bias. These two are parameter because the model estimates the value, optimal value for the weights and bias. And the activation function is also activation function hyperparameter. We can use whatever the activation. For example, in the case of hidden layer, still most of them they use the ReLU only. Why ReLU? The sigmoid function. When do I use sigmoid function? 0 and 1. In the case of classification, binary classification, this is good. But even in the case of binary classification, there are some cases they use in the hidden layer, they use ReLU. The reason is, supposing you are dealing with an image, you want to do some kind of image classification. In the case of image classification, how the system recognize the images? It recognizes the images by pixels. For example, you have 6 by 6 image. Okay, and here you have the pixels, right? 1, 2, 3, 4, 5, and 6. 6 by 6, pixel is there, and it will be like, 6 by 6, it will be there. So in that case, to if it converts the value between 0 and 1, what will happen is, any value, right? You cannot identify the objects that are part of this image. Hence, what it does is 0 to infinity. So now, with the leaky reload, or minus infinity to plus infinity, the reason is, each value here, 1, 255, and 3, each value in the pixel has some meaning in it. Supposing you have 3 is, I don't exactly remember it. 3 is kind of white color. 255 is something like, the gray color, something like that. Okay, so in the image, you should be knowing the color, everything. That is the reason why the upper value is going to be whatever the value returned in the previously, that one will be, leave it as it is. It is not going to convert, or it will not going to transform this value to fall anywhere between 0 and 1. Right, so because we are using ReLU, sigmoid function only convert the values to bound between 0 and 1, whereas ReLU is not like that, right? So 0 to infinity, any whatever value. With this output of your hidden layer, your subsequent layers can pick up this, and it can find out. Let's, in the real time scenario, we will be having more than one hidden layers. Multiple hidden layers will be there. Each hidden layer will gradually learn, new patterns. For example, the first hidden layer will identify the colors and other thing. Second hidden layer will identify the shapes. With the help of the shapes, it can, it can make out whether it is eyes, or nose, or lips, something like that. With that, it can learn. The next hidden layer will learn. Okay, this is the face, the human face. Okay, it's something like that. Okay, so in order to learn that, you should know the pixel value. Each pixel, see, each pixel has its own value. Okay, here each cell has its own value. Science, in the case of ReLU, the upper value is not going to get translated. Okay. Okay, so now you understood what are the types of activation functions are available. And the next one is the back propagation in neural network. How do we do the back propagation? What is back propagation? We'll take a look at it. In the case of neural network, so far we learned about what is forward propagation. Now we will take a look at the back propagation. It is the essence of neural network training. By doing the back propagation, we are going to fine tune the weights of the neural net based on the error rate obtained in the epoch. Epoch is nothing but your iteration. Okay, so in the case of back propagation in neural network, the gradient descent algorithm is used. Don't forget it. Okay, this is we can say this algorithm is probably the most fundamental building block in a neural network. The idea of this back propagation is to minimize the cost by adjusting network speeds. For example, this is your neural network. Okay, in this case, this is your forward propagation. So in this case, what the idea of back propagation, so what happens is, it picks up the error, and then it passes the error back. See, your input layer passes the values to your hidden layer. Hidden layer's output will be passed as an input to your output layer. Even the output layer, it does the same thing. Z equal to, this value into this one, and then it applies the activation function, and then only it gives us the final predicted probability. Okay, and once you get the predicted probability, in this case, is the predicted probability is the actual value, you get some error. So in this case, in output layer, we have two neurons. One is for class 1, other one is class 0. So what is the probability for class 1? What is the probability for class 2? when you add these two, right? Sorry, when you find out the error for these two, right? You will get the total error. So in the case of back propagation, what happens once the forward propagation is done? The idea of this one is to minimize the cost function, right? It tries to minimize the cost function, the error, by passing the error back, in terms of adjusting the weights of the previous layers. Okay, the level. So now by adjusting the value of the previous layer, right? But what happens in this case, iteratively it adjusts the values of the previous layers, and then it will try to reduce the error to the super minimum. Okay, it keep iterates as long as the it keep iterates by changing the values of the weights, and it will try to reduce the error to super minimum. So that is the whole objective of the back propagation. We want to find out the minimum value for the cost function, right? So now we will take a look at how exactly this one works. And here I have used some sample values for weights. Okay, and with this weights we will take a look at um, we will use the chain rule. With the chain rule we will try to write the we will write them the differentiation function, okay, using the chain rule. And then we will see how we can reduce the error by doing the back propagation, right? So in this case also the loss function is going to be your gradient descent algorithm only. You remember in the case of gradient descent, two important aspect. One is you need to remember the two aspect. The one is the gradient. You need to find out the gradient, and once the gradient is obtained, and and it has to know the step size, right? So the learning rate, you need to use it for the step size, and with the help of the learning rate, and by taking the product on the learning rate and the gradient, and if you subtract that value from the current weight, you will get the new weight. That is the whole idea of using this one. Before we jump in here, what I would suggest, right, we will take a look at chain rule, because you need to be familiar with the chain rule before we proceed with the writing the derivative for the gradient descent or back propagation. Okay, we have something called chain rule. You should be knowing about this chain rule before we proceed with that. The chain rule tells us how to find the derivative of a composite function. Okay, which means one function is nested over the other. And the second point is you need to understand, identify the inner function and the outer function. See, this works something like this. In the case of, for example, I want to find out dou y by dou x. Okay, which is nothing but find a derivative. I want to find out the derivative. For example, I have something called y is equivalent to 2x plus 1 to the power 6. This is the value I have it. And if I take the derivative dou y by dou x of this one, and how it works is the chain rule, the derivative of the outside function. You need to take the derivative of the outside function first, and then you need to multiply that outside function derivative value with the derivative of your inside function. I just write it here: derivative of outside function okay into the derivative of inside function. Okay, in this case, what is the derivative of this? First, we need to take the derivative of outside function, and then with that value, you need to take a product with the derivative or inside function's value. So in this case, what is the derivative of your outside function? In this case, the outside function is 6 here. Here you have 6 here. In this case, right, we what we need to do is to take the derivative to outside function. You need to know the power rule. We discussed about power rule, right? This one will come in front of this one. 6 into 2x plus 1 and 6 minus 1. The 2x plus 1 raised to the power 6 minus 1. This one will give you 5, 2x plus 1 to the power 5. Here you have 6 here. And then if you take the partial derivative on this one, what will happen? The partial derivative in this case, y is with respect to x's. This one, right? The partial derivative, since we are taking the partial derivative with respect to x, and the rest of the value will be considered as 0. So this one will become 0 and this one will go away. And you are left with only the 2x here, okay? And sorry, the coefficient of x is 2, right here. And here what will happen is 6 into 2x plus 1 into 2. The coefficient of your x is 2 here because we are taking the partial derivative with respect to x. This one will go away. Okay, 6 into 2x plus 2 will be there. Okay, so in this case, what will happen is, 12, right? So 12 into 2x, we can say like that, okay? But here 2x plus 1 will be there because we are not going to do anything inside of the function. We are going to leave it as it is. So 2 into 6, 12 into 2x plus 1. Okay, next one is we are, here what happened? We just took the derivative of your outside function. In this case, the power rule comes into picture. The 6 has to come in front. And okay, we did the outer thing, 6 here. And then the inner function, you need to take the derivative inside function. The derivative inside function, when you take the possible with respect to x, here what happens is 2 will, the 2 will come outside. This 2, because the coefficient of the x is 2 here, and 2 will come here. 6 into 2, 12 plus 2x plus 1 will come here, but we are taking the partial here. Ideally 12 into 2x will come here. So this is what you are this is how you need to use the chain rule, using which we can find out the derivative. So here the steps. The function must be a composite function for which, which means one function is nested over the other. Look here, this function is nested over the other outside function. And we need to find out the derivative of outer function, leaving the inner function as it is, and then find the derivative. Once you found the derivative of outside function, the next step is find the derivative of the inner function, the 2x plus 1, and multiply the results from steps 4 and 5. The inner function and then the outer function, you need to multiply it, and you will get this value. Okay, simplify the chain rule derivative. So once we simplify this one, we get this one. This is the value. This is the derivative for your dy by dx, dou y by dou x. Okay, so it is not a straightforward one, right? So you need to take the derivative of the outside function and then you need to multiply them. It's very simple. That's all. This is how it works. And what we are going to do is now we are going to use the chain rule, all the things to derive this one, to find out the derivative for this one. And we will see we're going to use the loss function gradient descent. With the gradient descent only, we'll be keep updating once you find out the gradient. And what we do is we take the product of the gradient with the learning rate, and then we subtract that from your current weight in order to get the new weight. Similarly, we do it for each and every the in the network, right? So each and every line, whatever the weights are there, we do it the same thing. So now what we will do is I just copy paste the same thing into the next slide. Where did I do that? Just, yeah, this is the one. For reference purpose, I just kept it here. So in this case, what we will do is we will calculate the net H1. So this is net H1 and out H1. Okay, here net O1, out O1, net O2. I have used some naming convention here so that while we take the while we do the derivation, we are not supposed to have any confusion. So here, what is the value for your net H1? Forward propagation. In the case of forward propagation, what is net H1? Net H1 is equivalent to W1 into your input 1. into your I1 plus W2 into I2 and B1 into 1. Here, look at the B bias is here because space is, I just put it here. B1 into 1. And if you simply plug in the value, you will get 0.15 into, here I say 0.05 plus W2 is your 0.2, 0.2 into 0.1 plus B1 is 1 into 0.35. Okay, and this one gives me 0.3775. Okay, and this one 0.3775. I'm not going to write it for everything because this one will get cluttered here. Okay, and then the next step is we need to use the activation function. This is the value of your net h1, which is nothing but z net h1. And now we need to apply activation function on this z value z. When you apply when you apply the activation function, what will happen? 1 divided by e to the power negative 0.3775, and this is the one 0.59 something will come. Okay, 593 something like that. Okay, this is what your out h1 value 0.593. This is what your out h1 value. So basically, the sigmoid function, in this case, we view the sigmoid function is used. The sigmoid function squashes the value between 0 and 1, right? So this, in this case, we are getting 0.593. And similarly, if you do the same thing for H2, you will get some value, right? So you need to multiply this one by this one plus this one by this one and bias into 1 into 3.5. You will get some value and you will get some other value here. So we're not going to write everything here, okay? It will take more time and it will be cluttered. Okay, we do the same thing for this net O1 and out O1. So what is the net O1 here? Net O1. We will just take, only this one, W5, this value into this one, out H1, plus the W6 into the out H2. Okay, yeah, out W6 into net 2 1. Yeah, for this one, it can't, it receives the input from these two things. Okay, W6 into the out H2 plus this is B2 into 1 because this bias is for your output layer. So B2 into 1. So what value we are getting it here? We are getting something like W5 is my 0.40 into my out H1 is 0.593 I mentioned, plus my W6 is 0.45 in this case into out H2. Out H2 is let's say some value, okay, 0.5968 something like 5968 plus 0.6 into 1. So if you solve this, you will get something like net O1, right? So net O1, you will get something like 1.105905, something like that. Okay, net O1. Okay, and you need to use the activation function. You need to apply the activation function on this value so that we will get something like 0.75. That is what I mentioned here, right? 0.75 536 something like that. Okay, and yeah, this is for my net O1, and the out O1 is this one. So net O1 gives me the z value. When you apply the activation function on this one, you will get this one. 7513. Yeah, this is the value 13 something like that, 75136 from here to here, here to here, and here, right? So this is the one gives us the predicted value, predicted probability as 0.5. The outro one gives us the predicted point 0.751. Similarly, we need to compute it for out 202. Okay, and this one and this one, and sorry, this one and this one, right? You need to take the product of this weight with this value and product of this value with this one, and then that value, for that value you need to apply the activation function. You will get a value for your outage 2, and then that value into this one and this one. Okay, and you will get the z value if you take the sum of these two weight and this value, right? And if you apply the activation function, you will get some other predicted value. In this case, the predicted value was given as 0.7729, I think so. I don't remember it. So this is the value. So now we need to calculate the total error, right? So here the total error is an E01 plus E02. That is what your total error. So in this case, the total error is your E total. One by two into target minus your output whole square. Output whole square in this case. So here it is nothing but the addition of these two things, E01 plus E02. Okay, and what is the E01? What is the error we are getting it? E01 is nothing but 1 by 2 into the actual is 0.01 minus 0.75136 or something like that. This is the one gives us the error as 0.2748. Okay, and similarly E02, if I compute it, E02 is, let's if you do the same thing, right? So 0.023, this is the error we are getting it. Now the objective here is when you add these two error, right? E1 plus E2, you will get, when you add these two values together, we get some total error 0.298. Now what we have to do is, this is the error. So the idea here is this error needs to be reduced. This is a cost. This cost function needs to be reduced. And how it can be reduced? Using gradient descent algorithm. So what we do is using back propagation. We call it back propagation. And so with back propagation, what we do is we pass the error from the output layer to the previous predecessor layer, and from the predecessor layer to the other layer, by changing adjusting the weights. In simple term, by keep changing the values for the weights, we will check at for which values of the weights the error is going to get reduced. This one we'll be doing it with a gradient descent. Okay, with the gradient descent algorithm, we'll be doing it. See, the idea of this one is to update each of the weights in the network, like how we did it. I demonstrated you in the linear regression, gradient descent for the linear regression, right? So in that case, what we do, we obtain the gradient. Once you obtain the gradient, we take the product of gradient with your learning rate, and then you subtract the value from your current weight. Thereby, we keep updating the weights in the network iteratively until the error becomes very, very small. Okay. Now what we will do is, to start with this, I just keep this as it is for our reference. I just copy and paste it in the next one. So now we'll start start with the output layer. For the back propagation, we'll start with the output layer. Now we wanted to know how much a change in W5 affects the total error. We go in the last layer, okay, and then what it is, gradually you move to the this layer, okay, and the input layer, okay. The first we'll start with the this layer, and here we are very particular. We wanted to know how much a change in W5 will affect the total error. So what is the total error? So now we need to take the partial derivative with respect to, so we need to take the partial derivative on the total with respect to dou W5. Dou E total divided by dou W5. We need to take the partial derivative on the cost function. You remember the same thing we did it there in linear regression, right? So with respect to W5. Okay, in this case, we are going to use the chain rule. Okay, we are going to use the chain rule. This is where the chain rule comes into picture. So in this case, the partial derivative of E total with respect to die, right? So we can also say this one, the gradient with respect to W5. By applying the chain rule, what we do, see in this case, I just tell you one simple thing. So this is your total, right? This total is, how you got this total? Because of applying the activation function. This total is depending on the out one, and the out one is depending on the net one, and the net one is depending on W5. If I write it here of the derivative, so this, this function, right? Sorry, this derivative can be this is a composite derivative function, which means this can be written as, we can write this with the different intermediary functions. Okay, here what I do is the total is depending on auto one, dou E total divided by dou auto one, because the error is depending on the auto one. So this is nothing but, this is a composite function. What is a composite? It's a nested function. This can be written like this. Okay, and auto one is depending on auto one into dou net O1 divided by, sorry, sorry, this auto one, right? So this one is depending on auto one. Here the auto one, dou auto one is depending on dou net O1 into this net O1 depends on dou W5. See, dou net O1 divided by dou W5. Okay. So if you look at only this part, right, you will be able to understand. Now we need to look at the total here. Now let us work on each and every derivative here, right? So this composite function or derivative, this composite derivative can be written as like this. Okay, to know the uh, how much change in W5 can affect the error. To know that, we have to use this composite function. This function, all right, for this we need to take the derivative like this, because we cannot directly take this one, because directly we cannot compute this one, right? We need to take the partial derivative with respect to this one, because this one is depending on this one and this one is depending on this one. And first we'll take a look at the E total. The E total we have already discussed, right? So the E total is nothing but E1 plus E2, the EO1 plus EO2. So this one off into 1 by 2 into target minus output squared plus 1 by 2 into target, I say O2, target O2 minus out O2. Simply plug in the value here. So in this case, I just take the partial derivative with respect to auto one, dou e total, because as per the gradient descent, right, we need to take the partial derivative with cost with respect to the last dou. First we need to find out, right? So dou auto one, in the dou auto one, how much change happened. So here, if you take the partial with respect to auto one, we don't have the auto one here. Hence, this part will become 0. This one will remain constant, and this one will get dropped because we don't have the auto one here, right? Because we are taking the partial derivative with respect to, we are taking the partial derivative e total with respect to auto one. We can see auto one only here. And in this case, you learned about the chain rule, right? So the power rule comes into picture. 2 will come here, 2 into 1 by 2, and your target minus out o 1, this 2 minus 1. We have taken the partial derivative. So we have taken the derivative on the outside function. Now we need to take the partial derivative on the inside function. So in this case, out o 1, what is the coefficient for out o 1? Into 1, right? So out o 1 is nothing but into 1. So which is nothing but minus 1. For the negative out o 1, the coefficient value is 1. Hence, when you take the derivative for this inside function, this one will go away, and you are left with minus 1 here. Okay, so here this one will get cancelled, and here the target out to 1, this is out to 1, target O1. Okay, here what is the target value? Target value is 0.01, already we have seen it, and here the out one is 0.75136. If you subtract this, you will get some value here. 0. How much you will get? 74 something, right? Something. If you 0.1 minus this one, will get 0.74136. This is the, likewise, we need to find out the value for each and every derivative here. Okay, so dou e total divided by dou out to 1. Okay, and then what is the next step? The next step is out to 1. What is out to 1? Up to this we are done, one step, and for this we are done, the 1, right? The 1 is over, and now we need to find out the value for the 2, and for the 2 out to 1. What is the out to 1? So here out to 1 is 1 by 1 plus activation function, right? Out to 1, 1 by 1 plus e to the power minus net over 1. The net over 1, whatever the z, right? The z, we take the activation function. So here, the out over 1 divided by, this is the 1. Then this is, what is this? This is what sigmoid function, right? Sigmoid function. When you take the partial derivative with your sigmoid function, what is the partial derivative here? So 0 out over 1 divided by dou net over 1. So dou net over 1. When you take the partial derivative on the sigmoid function, it will be something like sigma into 1 minus sigma dash into 1 minus sigma. So in this case, the out over 1. In this case, it is going to be your sigma is, see, this is nothing but this one, right? This one represents this one, and I call this a sigmoid here, out to 1 into 1 minus out to 1. Out to 1 into 1 minus out to 1. Here, what is the out to 1 here? The output of this one, right? Out to 1 is your 0.7536. Into 1 minus the same value, 0.75136, something like that. When you solve this, you will get something like 0.186, something like that. Okay, you get some value. So next one is this one, the do net O1 do W5. So this is your do out O1 by do net O1. We are done with this. Do out O1 divided by do net O1. We are done with this. Second part is over. Okay. The next one is the third part. So net O1. What is net O1? This net O1 is depending on what? The W5 into out H1 plus the W6 into, see this one is, for this the inputs are coming from here and here. For this the inputs are coming from here to here. So red color only, that's why I have given different colors here. So net O1 is nothing but W5 into your out H1 plus W6 into out H2. Out H2 plus the bias unit B2 into 1. If you plug in the value, you will get the value for this and do net O1. For example, do net O1 divided by do W5 is equivalent to, and here if you take the partial derivative, what will happen here? W5 1 the okay, so here the W5 is going to be 1 here. When you take the partial derivative, this W5 is going to, the coefficient of W5 is 1, right? And into out H1 out H1 into W5 to the power 1 minus 1. Chain rule. And the chain rule, the power rule also comes into picture. So here the W5, right? So to the power 1 is that one will come here, and out H1. Actually, sorry, the W5 to the power 1 is the 1 will come here. W5 to the power 1 minus 1, and then out H1. And then the next one is this one, right? So this part and this part, if you see here, we don't have W5 here, W6, and here the B2 bias 2 into 1. So this one will become constant, and these two terms will get dropped because we are taking the partial derivative with respect to W5. So hence, it will end here. So this one, what you get here finally. So here W5 to the power 1 minus 1, 0. Anything to the power 0 is 1. So 1 into 1 is 1 into out H1, which is nothing but out H1. Out H1 we already computed, right? So out H1, how much we computed? The previous slide, this is what, 0.593. Already we computed it as part of your forward pass. I've gone somewhere else. The previous one, right? 0.593. In between, so many things are there. Okay. There's something about 0.593. So we computed the values for all these three things. And for this, the output is this one. And for the second part, this is the one we are getting it. And for this derivative, we got this value. So now if you put all these three things, this is 1, this is 2, and this is 3. When you plug in these values here, so do E total, so do W5 divided by, sorry, here do W5 is equivalent to 0.7413 and 0.7413 into 0.186 into 0.593 is equivalent to you will get some value. Okay, so this is 0.082, something like that. Okay. Then what is the next step? Next step is we need to update the weights. In this case, the weight is W5. W5 is equivalent to W5 minus eta into the dou E total by dou W5. You remember this is the cost. What is the cost function in our case for this thing? Dou E total by dou W5. Dou E total divided by dou W5. For this, we got this value, right? All these three things put together, the I say this is A. We got the value for A as 0.082. So here, when you update this, this is the first iteration. What will happen is already the previous one is 0.40. 0.40 is the weight minus the eta is something like your learning rate. In this case, I say the learning rate is 0.5. You take a small value of your thing and 0.082. 0.082. Okay. So here, if you do the math here, you will get something like 0.35, something like that. Now we got the new weight, 0.35. So likewise, you need to take the partial derivative for all these things. The next step is we need to take the partial derivative for your hidden layer in order to get the what? In order to get the in order to yeah, you need to take the partial for your hidden layer. The same thing you need to do it here. Okay, so in this case, dou E total divided by dou W1. Okay, in that case, what will happen is we need to take the see in this case in this case the error, right? So the dou E total is depending on dou out H1 into dou out H1 is depending on your dou net H1, and your dou net H1 depends on your W1. Okay, you need to take the partial derivative. Right, so what will happen is when you do the partial derivative similarly for each and every weight, you will get new weight, right? So sorry, you will get the, when you take the partial derivative, you will get to know the gradient. Once you get the gradient, you can update the weight. In the first iteration, you are going to update the weights like this, and then you need to keep iterated. As long as for these weights, what is the error? With the adjusted weight in each iteration, the weights will be, you will get a new weights, updated weights. With these new weights, what is the error? By keep iterating it, we are going to check for which values of the weights the error is getting reduced, right? That is when we conclude that the algorithm has been converged. Okay, or in other words, we can say at which point in time we don't see any more improvement in terms of reducing the error. Okay, that is how we decide, when to terminate this loop. So based on the number of iterations, whatever you specified, it'll it'll get terminated. Either you can use the iterations like I discussed as part of the gradient boosting for classification and regression, right? So the it will get iterated as long as the condition whatever you specified, or the values iterations, the number of iterations whatever you specified it, or as long as once the error gets super minimum, it will get end, right? So that is how we need to, or based on the conditions whatever we specify. What the conditions? The iterations only. We need to keep playing around with the iterations for 10,000 iterations. What's initially you will get very less error for one iteration. One iteration itself we cannot decide it is really doing good job, right? So with multiple iterations, only we will get to know how much reduction error we can see it. So this is how it works, the back propagation algorithm. Okay, got it? This is very simple one. I just simplified this one. See, this total is depending on out one because we are getting the predicted value from auto one only, because in the auto one here the activation function is applied on this one. Once the activation function applied on this one, it will give us the value. That value is going to be, in this case it's a 0.753. But again, and the error is depending on this one. Now we need to compute the error. Error is depending on this one, and this one depending on the value emitted by this one, and then this one is depending on this one and this one. In order to find out the error with respect to W5, you need to go from here to here. This is how you can find out. Okay, so in the intro, they'll ask you the backward propagation, right? So how the back propagation works, they'll ask you, but we don't have to do anything for this. It is very simple. I just show you in the Jupyter notebook how to. In the case of Keras, we don't have to do anything. Like in the gradient descent, we have we have implemented the gradient descent using our logic, right? We have used our program. We did not use any built-in sklearn functions to implement the gradient descent. We have written our custom gradient descent. For the gradient descent, we have written our custom function. When it comes to back propagation, you don't have to write you don't have to write any function to implement the back propagation. It is taken care automatically by the Keras. What is Keras? Keras is an API to your TensorFlow. So, TensorFlow was developed by Google. They have something called Tensor Processing Unit. How many of you know the GPU? GPU is a graphical processing unit. The graphical processing unit is much faster than your CPU, 100 times faster than your CPU. And the Tensor, the Google, they developed an open source called TensorFlow. Right, TensorFlow, in order for their TensorFlow to run, right, they have developed something called TPU, Tensor Processing Unit. That is much faster than GPU. That is what the Google says. Anyhow, the TensorFlow is the backend. With TensorFlow, we can implement the deep learning related models in a pretty simple and effective way, and the performance is also much faster with TensorFlow. And what I do is I just show you. But Keras is built on top of the TensorFlow. With Keras, you don't have to write many lines of code in order to implement your neural network algorithm or something like that. Okay, it makes the developer life simple. But with the latest version of TensorFlow, they made it everything simple. It's a way they made our the developer life much simple. But you need to install the TensorFlow and Keras. It's working fine in the laptop itself, hence we don't have to go to Google Colab and all. We can do it here. If you want to test it in Google Colab, you can use it. Especially when we work with deep learning algorithms. If you want to use GPU and all, we can go and use it there. We cannot afford to have GPU in our laptop, which may be very costly. The same churn data set, I'm going to take it here. The reason why I'm using the same one is because you're already comfortable with this script. And also when you open this script, you should be able to see all the algorithms, how I implemented it. And the next session, what I will do is we have something called pipeline concept. Okay, and we will try to clean up, make our code more neat with the pipeline. You're not supposed to have the redundant code. Okay, so in this case, we have written, and I will show you how to create the pipeline, everything with the pipeline, how we can make our code more modular. Why it takes this much of time to load it? Okay, at last it was able to load it. Okay, let me just see. It's good, and the volume of the data is also less, hence it will be pretty faster. If I go down here, this is the one I'm talking about it. So TensorFlow, you need to install TensorFlow like this. Pip install TensorFlow, pip install Keras. And then once you install it, in my case, it got installed already. And next one is simply import like this. Import TensorFlow STF. In Keras models, import sequential. Layers, import. These are the things. These are the classes you need to import it from the Keras.models, layers, and optimizers. And you can see the model are equal to sequential. In a model, in Keras is sequential, okay, which is a linear stack of layers. Right, so the first thing we need to get right is to ensure that the input layer has the right number of inputs. How many number of columns are there? This is your kind of your input layer. Sorry, this is your input layer. First, you create the network, and then in the first layer of the network is going to be your input or input layer. This is your hidden layer, and this is your output layer. Output layer, you can see only one neuron here, right? So here you can, in this case, I have mentioned 18, which means 18 columns I have it. Hence, create 18 input neurons. I'm talking about this one, the blue colored one, right? So in this case, we have only two columns are there. Here I have 18 columns are there in the churn data. Hence, I just import all those things because this one take time. The fully connected layers are defined using the dense class. What is the dense class? They'll ask you. What is sequential? Sequential is it's a model which is a linear stack of layers in the case of Keras. And in this case, we need to keep stacking the one layer after another layer. The first layer is going to be your input layer. The input layer, we have something called input dim. So what is shape one will give you the number of columns, right? And here create 18 neurons for, and then the input dimension is going to be 18. The activation function is sigmoid, and then the hidden layer sigmoid, and the last one is also sigmoid. In this case, it's a classification thing, right? Binary classification. Hence, we are in a sigmoid is okay. And the next one is the LR 0.1 stochastic gradient descent. Learning rate is equal to 0.1. I mentioned it here. So this one, the last one, this is where we obtain the overall output classification from our network. Okay, this one is the layer 3, which is our output layer. And the here in this case, yeah, the model.compile. Okay, this is the steps that you need to follow if you want to implement the basic neural network using Keras. First one is you need to define the layer. Okay, how many input layer, hidden layer, and output layers are required. an output layer, in each layer how many number of neurons that you needed, what kind of activation function you need it in each layer, you need to define it, and then what is the um, loss function that you are going to, I mean the optimization function, gradient descent, batch gradient descent, stochastic gradient descent. In this case I mentioned about stochastic gradient descent. And the next step is, once you define your network, the next step is you need to use model.compile. Okay, and here the last function I mentioned, binary cross entropy. Okay, binary cross entropy is the loss of a function used in the case of binary classification. In the case of multi-class classification, category underscore cross entropy is used. Okay, the loss function. And the optimizer equal to a stochastic gradient descent. You need to specify the optimizer. The next one is the metrics, accuracy. Metrics is needed. And I just click on it here. Next one is fit. Oh, I did not execute this one. Okay, the next one is the fit. In the fit, we specify the data set, training data set, the input and output variables, and then epochs, how many number of iterations, and a batch equal to 4, right? So your batch. Any of this epochs and batch, I will explain you as part of the deep learning. Okay, don't worry. And the next one is the accuracy, model dot evaluate. So as usual, right? So the typically what we do is we initialize the instantiate the model, and then next step is we use the fit method, and then we predict, right? The similarly your fit, but in this case in between, it is little bit different here when it comes to Keras. First, you need to define the network design. This is kind of network design. You should be good with this one, especially when you work with the complex project. You should come up with the optimal number of values for the hidden layers neurons and output layer neurons. Okay, and then you need to specify the optimization function here. And next one is you need to define the loss function and using compile. After compile, you need to use the fit. Look, since we have mentioned 100 epochs is 100 iterations, it will happen. Okay, and then it automatically does the back propagation. In this case, when you use Keras, every after one forward pass, the backward propagation will happen. The here the accuracy. Well, look here, it's still going on because of 100 epochs. It takes some time. If you have less memory, what you can try with Google Colab. Okay, or else what you do is you can reduce the epochs 10 or something for learning purpose. Okay, here, what is the final error we are getting? See, earlier. Hmm, okay, now we are done. Okay, here we can see that how many number of epochs? 100, right? 97, 98, 99, and 100. So 99, we can see that 0.87 accuracy. The error is slightly increasing it here, right? So, yeah, so 3929 and 0.3770, after which the error is increasing it. Okay, try with 150 epochs and see. And I think this is the cutoff here, right? So you need to use this because after this, the error is increasing. Error should not increase. Instead, accuracy should increase. But the error accuracy is increasing, but how come the loss is more than this one? Accuracy is 0.87. No, no, no. The accuracy is decreasing, right? 8712 is actually obviously less than this one. So here, this is the one. So it is converging at the 99th epoch. Epoch is kind of iteration. Batch, I will tell you later. The next one is accuracy. We are able to get a 0.86, 0.87, close to that point. This one is 0.386. Yeah, probably we can stop the, we can use the 99 as an epoch so that your accuracy will be getting this one. Okay, but here in this case, it is taking the average, it seems. Yeah, average here, average of all the things. Okay, and the next one is the compile here. Evaluate will give you the accuracy and the error loss. And the next one is the here also I've used. Okay, okay. In this case, what happened? This is an additional step. Instead of using stochastic gradient descent, we have something called Adam optimizer, like batch gradient descent, stochastic gradient. We have some Adam optimizer. With Adam optimizer, we will see what is the accuracy we are going to get it. compile, fit, and then evaluate. That's all. These are the steps that you need to remember it when it comes to Keras. The first step is you need to use sequential, right? Once you use the sequential class, you can define the network, right? So how many input layers are here, how many how many neurons should be there in the input layer, how many hidden layers are required, how many output layer, how many neurons are required. You can define it, first step. Second step is the compile. You need to compile. In the compile, you need to specify the loss function, the binary cross entropy for binary categorical variable, and then fit. Okay, and then the last step is evaluate. That's all. But here I just went one step ahead and to see with the Adam optimizer, can I see any improvement? Uh, the the here we don't see much improvement, right? So here, let me just see here. Okay, here the accuracy is 0.87 training and the test is 0.86. 0.87 is good, right? Yeah, 0.87 is good. Here 0.8696, there is a slight improvement here with Adam optimization. Fine, this is how you can implement the neural network using Keras, because nowadays the TensorFlow is very popular with TensorFlow, and we have something called um, for TensorFlow, the competitor for TensorFlow is PyTorch. Okay, and PyTorch, I have not used much. We did some POC, but I did not use it much. But if you know the TensorFlow and Keras, that is more than sufficient. Okay, any questions so far?